let me introduce Michael Pyrcz. I'm thrilled to have him here. I've known him for a while. We wanted to get him to give a talk. I think there was some cancellation that happened because of the winter storm, but here he is now. He's a professor in multiple departments. He's a professor in the Department of Petroleum and Geosystems Engineering, and also the Department of Geological Sciences in the Jackson School. That just messed up my notes.
Oh, no, sorry. Okay, are you good now, Adam? Are you good?
Oh, yeah, no, I'm good now. Don't worry. You have so many affiliations that I actually had to have a cheat sheet for that. So you're in Cockrell School, you're in the Jackson School, and you worked for Chevron for 13 years. You were the lead researcher on reservoir data analytics. Anything involving spatial data analytics, geostatistics. I mean, Michael knows about it. You're also the associate director for the Center of Subsurface Engineering and the Environment. And Michael's a great teacher. He's starting or at least, I don't know how far along you are on he's doing the freshman research initiative at UT in energy data analytics. That's a major undertaking. And you can check out you can go to his website, michaelpyrcz.com, or check out his course lectures on YouTube. His channel name is GeoStatsGuy Lectures. So that should be fun to look at, but it's great to have you here, Michael. Let me, thanks for coming. And today he's going to talk about data analytics and machine learning for subsurface engineering and geosciences, and anything you want to correct there, please go ahead, but thanks for being here.
Adam, thank you very much for the very kind and thoughtful introduction. I do appreciate that. I apologize for messing up your notes. I got too excited. I want to share the slides. But no, thank you very much for that. It is my pleasure to be here. I really do appreciate the Machine Learning Lab. It's just been a wonderful association. I will comment on the fact that I am one of the core faculty in the lab. I'm proud of that. I think it's a wonderful undertaking, and I do appreciate Verena and Adam for leading this. We also have Professor Damascus here, who's also one of the leaders of the center, and I just appreciate the opportunity. I want to acknowledge, I'm going to show a bunch of stuff. I can't come and talk about machine learning and not show a bunch of machine learning and data analytics too in the subsurface. I want to acknowledge that I'm going to show work from my students. And so I've listed a bunch of them here. I think there's actually some of the students I missed, but I will be showing a bunch of work from my students, and I'll credit them on their work when I get to it. Also, because I do collaborate a lot. I have 16, I think now, graduate students. And I think most of them,
Did you say 16 or 6?
Yes, 16. And,
oh my gosh.
I believe basically 70% of them or so are co-supervised with other faculty, because I believe in what I do is very integrated. But I'm having a lot of fun doing it. I want to acknowledge these other professors who I work with, whose work I'll be showing. What's my motivation? Well, I have a scheme. If I was a supervillain, I would be stroking a white cat right now, thinking about my scheme. And what it is I have a message. The message is the subsurface needs new capabilities and solutions to fully realize value in the digital revolution. And guess what? That's good. We got a lot of good work for us to do. Now, geoscience and subsurface engineering remains critical and will have enhanced impact in the digital revolution. We'll have digital augmented workflows. I like to say geoscientists will do more, and they will have more time to do geoscience. Engineers will have more time to do engineering and will have more impact. But we need to build on a foundation of geostatistics, spatial data analytics. Now, let me pause there. Adam, Verena, and I, we all agreed if anybody has questions or comments throughout, please unmute, jump in. Also, I notice everyone's turned off their videos. If you want to turn your videos on and interact with me, I love it. I get kind of lonely up here. And so I can see looks of astonishment. I may ask questions and people can gesture or jump in. Randy, thank you very much for jumping in. I appreciate that. Thank you. Everyone else.
I'm astonished you have 16 students.
What's that?
I'm astonished you have 16 students.
I work 7 days a week. It's just crazy. Yeah, it is kind of crazy. But anyway, but it's great. We're doing really interesting things. I'm excited. Okay, appreciation. Of course, thank you for the invite. It is my pleasure to be here. I'm one of the core faculty and I'm very proud of this group. And I do like to talk about you guys wherever I go. I do appreciate the ability to work and have partnerships through the center. We're kicking off new stuff in mining. You forgot to mention, Adam, I'm a mining engineer by degree. My first degree was mining engineering. And so we're doing stuff in all kinds of subsurface problems. Fantastic group. You're putting together things all over the 40 acres. All right. Thank you. Thank you. Okay, this is what I'm going to cover. I promise only like maybe 4 slides of bragging. No, just about myself a little bit, sharing resources, and then I will get technical. Subsurface data analytics and machine learning. I'm going to convince you that subsurface is different. It's unique. It needs new solutions. And I'm going to tell you about how we can build from what we already know. Let me do that. First of all, if you've never met me in person and you're still unsure about my name, just say it like that, Pyrcz, and it's perfect. You say it as well as I do. 13 years of practical experience. Everything I talk about, I've done in industry. I actually, by the time I left Chevron's technology research center, basically I was leading a large research program, several millions of dollars per year. I was selling research. I was communicating research. We were solving problems. It was very exciting. I'm very active on social media. Anybody here on the call on Twitter? All right. Hey, I saw you there recently. Verena, I'm going to follow you. Right after this, I'm going to follow you, okay? So no, very cool. Good to see that. I do share resources on social media, on Twitter, GitHub. I share an awful lot. Geostats Guide lectures, all of my lectures from the university linked to the GitHub account. You can follow along. Data analytics, geostats, and machine learning workflows. You can follow along with us. I'm very much committed to creating educational content that is highly interactive. These are examples right here explaining fundamental spatial data analytics concepts, interactive dashboards in Python. I do that. I'm really getting excited about that. It's just too much fun. So I do a lot very interactively, and I do have a package. Anybody here interested in contributing to open source? Anybody do that? Jump in. I have a package which I authored, and co-authorship is very cheap. Just go ahead and jump in, help with documentation, help with code quality, help with speedups, anything. It's a Python package for geostatistics, spatial data analytics. All right, that's enough of that. I do have a team of students, added 3 just recently, and a couple of graduating, so numbers in flux. But we have a group, we're doing a lot of work. If you want to hear about consortiums, I'm interested to talk. And I teach a lot off campus. If you are from off campus, I taught 1,700 working professionals last year alone. 44 engagements. I'm always teaching off campus and happy to come visit you. Okay, that's it. I promise, no more shameless self-promotion. I want to give you a little bit of an overview of data analytics and machine learning. Now I look at this group and I'm looking at some names here, and I'm pretty sure we got a lot of experts. And so please just suffer this. I want to make sure we're together in terminology and concepts before I move forward. First of all, statistics. Let's define it. Collecting, organizing, interpreting data, drawing conclusions, and supporting decision-making, or we don't add value. Okay, so that's what statistics is all about. Data analytics, if you Google search that, it's always like something about analysis of data to support decision-making, maybe business data analytics, maybe big data analytics. Would you all agree with me that data analytics is statistics? Anybody want to disagree on that? We could have a debate. I really think they're the same. I think there's some rebranding going on. Geostatistics is a branch of applied statistics, dealing with spatial, temporal, multivariate data, uncertainty, spatial continuity, volume support, all of those things. Now, what I would say is geostatistics is essentially, it's an essential component of spatial data analytics. And if I had to draw a Venn diagram to describe these scientific disciplines, big data, statistics, big data analytics, spatial big data analytics right there. I wish I would have wrote that book. Somebody beat me to it. That book just came out. Too bad. That's a great name.
No, I disagree with you, Michael, because I'm willing to bet that you run algorithms, right? Yeah, and so, you know, traditionally algorithms would not be considered a part of statistics. So I don't agree with you.
Now I'm going to disagree with you, Adam, and this is a friendly disagreement. I do like the definition from James et al. And Hastie et al. Of statistical learning. I like the idea of machine learning, in fact, is a statistical model, and it's a statistical learning. And so based on that, I would suggest that that includes algorithms, but I'm comfortable if we want to divide it up.
Okay.
All right, all right.
An argument for another time.
Yeah, and it would be a fun debate. It'd be a fun debate. Regardless, I do think that the data analytics versus statistics, there's nuance there. It's a bit challenged. Machine learning, I Google searched it just like many people do. I got the Wikipedia site, a toolkit, algorithms, and thank you, Adam, you reminded us of that. Algorithms, mathematical models that computer systems use to progressively improve their performance on specific tasks they're learning. They build the mathematical model on sample data. Training data is essential. Those are the three components so far, without being explicitly programmed to perform that task. Generalizable. These are a toolkit of methods that learn on data and can work on a variety of problems. Okay, now what's interesting, if you read to the end of the article, you're going to find a statement like this: where it is infeasible to develop an algorithm of specific instructions for performing the task. What does that mean? If you know the engineering physics, if you know the geoscience physics, we should use that. And I think a really good quote from Dr. Taurus Verdin was this: don't use data-driven approaches as a crutch because you don't understand the natural setting. It should be a combination. Okay, that's one comment I make. Every time I think about machine learning, I think about this equation right here. It really does come down to using a set of predictor features, the inputs, and trying to map them across. It can be very complicated, of course, to the response features, a functional form, a relationship that's trying to mimic the natural setting. That's the main approach of predictive machine learning. The idea of building a predictive machine learning model is usually this type of process right here. I tried to do it all on one slide. This is the test train approach. Now I know there's people here who are, no, I do train, validate, and test. I'm just talking about the simpler workflow right here. Split the data into train and test subsets. You take the train data, the solid circles, and you hide them away. You're not allowed to look at them. You find that place in your office, you don't go anymore. You know the pile of papers? All of us professors have those, right? You take the testing data and you put it there. You're not allowed to look at it. Now what you do is you train with the training data, the model parameters. You train a simple model, you get the best fit with the training data. You train a more complicated model, and you keep going. You get the best fit models, and now you go back to your office, to that place with all the dust and the pile of papers, and you find the testing data. You bring it back. And you see how you perform with regard to the testing data. You pick the model where you get the best performance. This is hyperparameter tuning, finding the best complexity. Why do we do that? If we didn't do that, we would invariably pick the most complicated model. We would be in the most overfit situation, which is very dangerous. In fact, how am I doing at the testing locations with my most complicated 7th order polynomial model? I owe you an apology. I punched a hole through your floor. I'm pretty sure it's gone through the bottom of the monitor, it's into your foundation. It's a very bad model. And so this is helping us avoid overfit. Let me just comment on a couple of definitions quickly here and move on. Model parameters, those are fit during the training stage with training data in a 3rd order polynomial, B3, B2, B1C. Very simple. These are the model parameters. They change the slope, the form, the fit to the training data. The model hyperparameters, those are totally different. They constrain the model complexity. Our choice of 1st order, 3rd, 5th, 7th order polynomial, that's our hyperparameter in this case. Now, this is going to control the complexity, the degree of flexibility of our model. Why do we do all this? And this is like my last slide of these basics. We're avoiding model overfit. If we create a simple model and we look at its error in training, we will have high error usually. As we increase the complexity, error in training will continue to go down. You will have more flexibility. You will get to a point where at some level of complexity, you are likely able to perfectly fit the training data. The testing error will generally fall too, but at some point will start rising up again. The zone of overfit is when you start to have worse accuracy in testing as you add complexity. An example of a decision tree model with one predictor feature, one response, completely overfit, perfect accuracy at the training data, probably terrible between the data. And here's a more moderately fit, probably more optimum model. Okay, what did we learn? I think data analytics is statistics, and we can debate that. Spatial data analytics is geostatistics, and we could debate that too. There's aspects of spatial statistics, spatial point processes, people would argue are separate. Geostats would just embrace them. I think we're fine. Okay. Let's talk about subsurface data analytics and machine learning. Why are we different? Well, first of all, if nobody has ever done this before, please let it be my honor to welcome you to the fourth paradigm of scientific discovery. The first paradigm of scientific discovery, we've been doing that forever. Experiments to observe the natural systems, to understand what's going on around us. The Egyptians were doing things before that too. Second paradigm, theoretical science. Now we realized we could find fundamental laws, fit equations. Third paradigm, computational science. The world is heterogeneous, complicated geometries, multiple interacted coupled types of equations and relationships. We needed a continuum mechanics, and we needed more complicated systems to do that. Fourth paradigm, realizing we could look at the data on its own, detect patterns, anomalies, structures, everything that we're doing in artificial intelligence or machine learning. This is fourth paradigm. And we could also argue about when it started. We're not alone. The subsurface people are working on this right now. The data transformations are underway. I go to many subsurface oriented companies, and every one of them has a brand new division working on data science, data analytics, and machine learning. They're all looking very quickly. They're trying to move forward. In fact, if you look at the Deloitte study on readiness across different sectors of our economy back in 2019, they suggested that energy, which is good, it's representative of the subsurface, is in the middle of the pack as far as proportion of organizations with high maturity. Who's winning? TMT. That's not a surprise, right? Tech, media, telecom. They're leading as far as adoption. Healthcare and life sciences are trailing. All right, so everyone's working on this right now. I have biases. My biases are there's opportunities to do more of our data regardless. The other thing, there's opportunities to teach data analytics and machine learning methods to engineers and geoscientists, and I do it all the time, and they learn well. They improve their capabilities, they do great. Geoscience and engineering will remain core to the subsurface. I will defend that statement. I'm going to show you examples right away. When we're working in the fourth paradigm, let's just remember, we do not abandon the previous paradigms. The second paradigm is all based on the first paradigm. The third paradigm, anybody who builds numerical models knows that they're a combination of theoretical and empirical. So we know that we build on, we augment, we don't throw away our old paradigms. We're not going to replace them. We're going to augment the fourth paradigm on top. Okay, the subsurface is different. Let me try to give you an example and explain why. First of all, the subsurface deals with sparse, highly uncertain data with complicated, heterogeneous, and what Oreskes and all would call open earth systems. Okay, how sparse is our data? Anybody here know? What proportion of the subsurface do you think we sample directly with wells, cores, well logs, drill holes, and mining? If you're thinking, oh, somebody put something in the chat window. I'm kind of excited there. Let me see, where's the chat window? Oh, I thought I can't find the chat window.
Less than 1%.
Adam, thank you very much for helping out. I appreciate it. Okay. Anuj, I agree with you. 1 trillionth. 1 trillionth is commonly, volumetrically, the proportion that we sample. 1 trillionth. Okay, so let's just imagine that. That is challenging. That's sparse data. High degree of necessary geoscience and engineering interpretation and physics. Did you know that there's not a single type of data from the subsurface that we can use in the raw form? They all need engineering, physics, geoscience, interpretation, and physics. They all need that. And we have expensive, high-value decisions that must be supported. Gulf of Mexico, a deep water well with well test. How much does it cost? Anyone? One well. 200 million, 300 million?
A billion.
Okay, Adam, you're a little high. You're a little high, but I'll tell you what, order of magnitude, you're there. A lot of money. If you're thinking 100 to 200, depending on the location, the complexity, the depth, and so forth, you're in the right ballpark. It depends also on market. But yeah, 100 million, 200 million, that's what we're talking about. Okay, these are expensive, high value decisions that must be supported. Let's compare that to a common application of deep learning, the recommender engine. Anybody here use Spotify? I see that. Verena, I appreciate that. Thank you very much. I use it too. This is my Spotify account. I hope this is not too much information from the summer of 2019. You guys all see I'm Canadian. I listen to a bunch of Canadian music. It shows up on the recommendations from the recommender engine. Okay. Every once in a while, a song comes on and I start tapping my foot and I start nodding my head. It's got hard rock. It's kind of got a hook to it. And then partway through, I catch myself and I go, darn, it's Nickelback again. Okay. I want to tell you, I apologize on behalf of Canada for Nickelback and Justin Bieber. Okay. I'm sorry. We're sorry. Do you believe me? I don't like Nickelback. What we all did before, but I don't like it anymore. Would you agree with me that that's a case of the recommender engine getting it totally wrong? Okay, what is the cost of Spotify giving me the wrong song? I see the look on your face. You don't believe me. You think I like Nickelback. What's the cost of that? Would it make any sense for me to have a personal DJ in my office on the 40 acres playing music for me? Would that be value? Cost of my happiness. That's the quote of the week. I am going to use that. Thank you very much. Personal communication saying. All right. Thank you. That was funny. It would make no sense at all. That's low value. We need to develop novel subsurface data analytics and machine learning solutions because we need to integrate this geoscience knowledge. We need to deal with sparse data and we need to defend our $200 million decisions of where to put a well. Okay. Subsurface data-driven technology is mature. I want to convince you of that. The historical perspective of this is very interesting. You can go back to Kolmogorov and look at the fundamental axioms in probability and the initial ideas around stationarity. Then you can go to Danny Krieg in South Africa in the 1950s, developing the initial ideas of geostatistics. Volume variance, spatial continuity, spatial estimation with uncertainty. Then we have Matheron, who developed the theory on top of the practice of geostatistics, inventing geostatistics and mathematical morphology. I wish I invented two sciences. That's very cool. Next, we go to Janelle Verley and my PhD advisor, Deutsch, who really worked hard to make these approaches practical for the subsurface resources of all types. And now we have the current day. We have a rich history in working in big data analytics and statistical learning, geostatistical methodologies. The subsurface, I would say, has been big data, data-driven long before tech even learned what big data was. And you might say I only smack talk like that in front of you guys. My last meeting with Google, I told them that. I told them they should listen. What would I teach somebody who came from data science, machine learning, computer science? What would I teach them so they could understand the subsurface? I would teach them about geostatistics, spatial data analytics, and they would see that there is a whole wealth of concepts that are very powerful and augment very well the data-driven approaches, okay? And you know what they would learn? I got to tell you, we do the Freshman Research Initiative in Natural Sciences, and we ran a hackathon in petroleum and geosystems engineering just last month. The top team, the Roaring Kitties, had 3 students from natural sciences who were using these types of concepts and did very well. Okay, so, and they also had some petroleum engineers helping out. Okay, verification and validation of numerical models of natural systems is impossible and much harder in the subsurface. Subsurface is unique and even more challenging. We need to develop new technologies. Let's build on the foundations of geostatistics and spatial data analytics. Let's do that together. I'm going to walk through probably like 10 different examples of using machine learning and data analytics in the subsurface, and I'm going to share some learnings from that. Okay, let me pause there. Everybody good? How's your energy? People are still good? You're with me? Adam, all right, Levent, I appreciate the double thumbs up. That's an A for that. Emily, I appreciate the thumbs up too. Thank you very much. Thank you. All right, let's talk about data interpretation. Who here has ever worked with well logs, well cores, drill holes? All right, we got somebody. Are you from the geosystems? Are you from petroleum or from geology? Levent?
I'm from geology, yes.
All right, well, welcome to you. Thank you very much for joining
Thank you.
in. And
Thank
you
you.
know, as I'm talking, you jump in here if I get anything wrong, okay? I'm half a geoscientist, but I'm half an engineer. Okay. If we look at these wells, when we cut a one-dimensional path through the subsurface, we use different methodologies such as extraction of the rock, and we also use remote sensing type of well logging technologies where we try to use the physics of the rock fluid system to make observations. When we do that, the geoscientists know that there are common motifs, there are common types of patterns that occur in the subsurface. And they're beautiful. Anybody here ever been to a rock outcrop? Anybody drove through Austin and looked at some of these road cuts? Anybody gone down the river and looked at the cliffs? That is the Glen Rose Formation. That's carbonates. You can actually see and understand those structures. They're fascinating. Well, you can take those structures and you can train a convolutional neural net. You can train the convolutional neural net, and now it can detect those types of patterns within your data. This is what we learned. No matter how hard we worked at that, we learned that we still needed to do feature engineering. We did a better job when we took multiple well logs and we combined them together using physics of the rock system to say, no, those are giving us indirect measures of rock quality. And now we'll turn it into rock quality, and we feed that into the convolutional neural net. The closer
Michael,
we could get.
what specifically were you trying to predict there with the network?
Awesome, Adam. I do appreciate that. What we were trying to do was we were trying to go with well logs, and we were trying to find what would be the specific classes, the classification of different types of rock that we could use then to be able to map away from the wells. Okay, so we go back here to this image. We could take a look at this. If we could classify that, recognize that within a well log, we could say, okay, that's a prograding marine setting. So now we would expect, if we move basinward, we would expect to see the same type of rock, and we would expect its extent to be on the order of this many kilometers. We would expect that to be this type of volume or this type of quality of rock if we're worried about, even if we want to do alluvial diamonds, the grades of the diamonds we'd expect to see and so forth. All right, Adam, does that help?
Yeah, someone commented lithologies.
Exactly, nailed it. Facies, lithologies. Now, when we talk about facies, we could be talking about lithofacies, depofacies, which are kind of larger scale kind of geometries. And so there's different scales we could be looking at the problem. In this case, we were mainly focused on lithofacies and what we call depofacies. These right here are examples of depofacies. I do appreciate the geoscience questions. Thank you. All right, and what we found, and I think the geoscientists will respect this, is that we found we needed feature engineering, but we also needed to put in a framework. We needed to put some type of guidance in. In other words, if we were working across an entire unit, like a depth, this is in feet, and now we have 350 feet of depth right here, we found we did much better if we broke up the problem. In other words, we said, we know from other source of information that this zone R35 is different from R30. Providing that type of conditioning into the model had a great increase in our prediction accuracy. When we tried to mix it all together, we found that we had a lot of issues. And so we think that the interpretation combined with the machine is essential for accuracy. Now, just like geostatistics, we need to build our deep learning models within a geoscience and engineering framework. It doesn't do well if we just try to throw all the rock at the machine, mix everything together. Okay, and I'll comment on that a little bit later too. Spatially aware feature engineering. This is very interesting. It turns out that when we drill a well and we produce fluids from the subsurface, what we are doing is we're sampling a volume of the subsurface. The fluids are being produced from that rock. We're seeing a large volume. You see that cylinder right there? Now, it would make a lot of sense if we could somehow summarize the rock over that cylinder. And so what we did is we came up with a new feature. And the feature is based on a concept that's very interesting. It's called dispersion variance. Dispersion variance is a spatial variance. It's a generalized form of variance. And what it does, it allows us to characterize the amount of heterogeneity or change we would expect to see in that cylinder as a function of the size of the rock volume and the spatial continuity. You see these lines right here? That's spatial continuity, that's heterogeneity in the subsurface. And if you change the dip of the well, you change the orientation of that cylinder, it results in a different amount of heterogeneity or variance. And so we were able to characterize that. This is a function right here that represents for different dips and angles. As you change the dip and the angle of the well, you change the degree of heterogeneity you'd expect to see. You can minimize heterogeneity if you drill in the same direction as the major direction of continuity in the subsurface. And that commonly occurs. We can do that. Anyway, what we can do is we can use this as a new feature in our machine learning models to aid our ability to build good prediction models. And we found this actually works quite well. It's a new engineering feature that accounts for scale. Feature engineering is critical for machine learning, and geostatistical measures are really good at providing new features to put in our machines. They're spatially aware. Let me talk about dynamic time warping. This is a very straightforward process. What we're trying to do is we're trying to map signals. We have an input signal, the blue signal right here, and we have an output signal, the orange signal, and we're trying to map them across, the blue to the green. We identify this is the location here we can map across to. This approach of signal matching is pretty useful. It's often used in one-dimensional temporal information. What we're doing is we're using it to try to understand if I have an injector where I'm injecting fluids and I have a producer at another location where I'm producing fluids, I can try to map across. Where does the water get injected? Where is the oil being produced? And I can start to try to see what is the time lag? What is the time it takes for me to see the first response to my injection in the production? Now, this dynamic time warping approach is generally done by using a cumulative cost matrix. And what we do is we then find the path of lowest cost through that matrix. Now, the general approach, when it's applied, can have horizontal and vertical lines. It's a mapping of from the one signal to the other. In other words, the water injection, the input, to the output, the oil production. Now, if you have a horizontal or vertical line, if I do the projection and I show it, what that's equivalent to is basically projecting from an interval to a point on the other signal. Now, that makes sense if we're trying to do something like stratigraphic and we're trying to map and we have discontinuities, but for flow, that doesn't make any sense because flow would not have a discontinuity like that. And so what we've done is we start to work with these and we start to impose physics-based constraints in this mapping. In other words, we would expect that there should be some offset here due to the separation and long scale continuity between wells. And we would expect that there's a constraint on these slopes right here due to the specific amount of diffusion we expect to see with regard to the short scale heterogeneity. By doing this, we can improve this mapping. It becomes a dynamic time warping that's physics informed using subsurface information. So we have plausible data-driven methods for subsurface decision-making that are now constrained by the geoscience and engineering constraints, their information and their physics. We think that's important. Okay, garbage in, garbage out. You ever heard that phrase before? Would you believe that's still true of machine learning? You ever tried training with really bad training information and then try using it on something different? What we're interested in is bias in, bias out. I'm going to make a really strong statement. Most spatial, sparsely sampled data sets are biased. Do you believe me? We do not drill at $100 million a well for the purpose of random sampling. Would you agree with that? We drill to reduce uncertainty and to maximize profit. By definition, bias sampling. Okay, let's talk about that. I sat down with one of my graduate students, Wendy Liu, and we asked the question, we know our data is biased. If we train our machines with biased data, do we get biased machines? So what we did was we took a spatial data set, X and Y. This is spatial data. Does everybody see that this is biased? Can you see? Can you put your bias glasses on? Can you see it? The purples are the high values. The lighter colors are the lower values. Do you see how we've oversampled the good locations? This happens all the time in the subsurface. Now we have an example here with less bias, and this is regular sampling. By definition, should be, unless we have an alignment with a periodicity, should actually be an unbiased sample. Now what we do is we build a decision tree. This is super simple. We're doing it for data imputation of TOC, total organic carbon, using porosity and fraction of clay. We build a decision tree with regular, uniformly weighted data. We build a decision tree where the size of the circles is based on the data weighting. The data weighting comes from declustering. Here's a little information about declustering. When we do this, something very interesting happens. What we find is that the conventional decision tree approach, we picked a very basic model so we could just demonstrate it. We did it on random forest, we did it on more complicated models, we get the same results. The conventional decision tree model, as you increase the bias in the data set, the bias goes up dramatically in predictions from the tree that we built. Now, here's what's fascinating. We trained with biased data. We tested with unbiased data. The signal of bias was preserved in the model. And I think that this is very important. Okay. Now, when you do a weighted machine learning method, you significantly decrease that bias. It goes pretty far to mitigating that problem. In expectation, we show right here the improvement, and we show that there are some cases where you make it worse. If I told you I had a method for automatic debiasing that would always make it better, I should be selling you snake oil too at the same time. You can't ever guarantee for every pathological data bias case that I can solve it. But in general, it greatly improves it. We recommend that we debias our machines in spatial data sets. Okay, so we need to debias these machines going forward. That's what we really do. We've seen this in many, many cases. Anomalies are impactful. What about spatial anomalies? I am really worried about anomalies. Would you agree that we have many issues with data? That we have many reasons that we can have blunders with data? Data can get messed up. When you deal with the subsurface, you deal with another additional problem. That's known as non-stationarity. Things in the subsurface change. Where's my geoscientist? Discontinuities, unconformities, transitions. They happen all the time. What we want is we want a tool by which we can find spatial anomalies. We've developed a methodology based on the varogram. I'm not going to go into the details, but a varogram model actually provides a full bivariate probability density for any distance and direction offset in your data set. In other words, from this data to this data, I can calculate the full PDF. Then I can actually calculate the probability or likelihood from that PDF, like a alpha level. What I can do then is I can assign a likelihood. So I can go through all of my spatial data pair by pair to the nearest neighbors, and I can identify a likelihood right here going from very low likelihood of occurrence to high likelihood of occurrence here. I can look through my spatial data and I can find, look at this data point right here. You see it's purple? That indicates that there's probably a blunder. There's a problem there with that spatial data. Right here, this entire region might be non-stationary. There might be a transition or change. This is essential. Detecting and identifying and removing or treating outliers is essential with spatial data. We know when we build machine learning models that if we do a lot of multimodal, we mix in a lot of outliers, things can be very sensitive. Just imagine the covariance matrix if you're just doing a PCA operation and you start throwing in outliers, you're going to blow that apart. That's not going to work. And so we need to be more careful. What about geostatistical significance? I know I have students working on multimodal spatial modeling. You know what my preference is? Avoid it if we can. If we can break up the spatial data set into unique populations, that's very powerful. Improves our prediction models. We can also use conditional methods. Yes. What we've done is we've looked at taking the concept of statistical significance and extending it to spatial geostatistical significance. What we're able to do now is that the methodology we're using is the spatial bootstrap resampling approach. We can account for conditioning information. We can account for non-stationarities. And what we can do is take the information from pad 1, a subset of the data, pad 2, well pad 2, subset of the data. We can look at their specific plots, and we can see the sampling null distributions by resampling with Spatial Bootstrap. And we can look at this and say, nope, that's not significantly different. This pad and this pad appear to come from the same population. We can mix that data set together. I think this could be very powerful for establishing what data we should be using for training. Okay, let's talk about, we need to use geostatistical methodologies to establish and understand stationarity. I think more work needs to be done on non-stationarity with deep learning, machine learning methodologies. We're working on that right now. I think there's a lot of unsolved problems around it, but if we can separate things into stationary domains, that's very powerful. More spatial data analytics for subsurface data-driven methodologies. In this region, this scope, I think it's really important to use spatial data analytics. I think it's important to use spatial point processes and different types of spatial statistics. Here's an example right here where we're sampling fractures from an outcrop. We're able to use the K function, the Ripley K function, to characterize the multi-scale clustering and anti-clustering behaviors in a non-stationary manner. And what we can do then is we can take that and we can simulate and make our own data sets for training deep learning. We can also do data imputation. We can also detect anomalous circumstances. So we've been doing a lot around spatial data analytics to improve our ability to quantify subsurface phenomenon, in this case, fractures in an outcrop. All right, spatial statistics is a powerful new lens to explore the subsurface. Okay, now I need to get into some deep learning or ML is going to throw me out. I know that. I know people are going to get impatient with me. You'll see my bias. My bias is we build from fundamental data analytics and statistics concepts. Modeling with machine learning requires good training models. We know that. Would you believe that this is a huge challenge in the subsurface? What are, anybody in geoscience, what are our available training models, training data sets within the subsurface? Where do they come from?
I would assume probably seismic data.
High resolution seismic data, agreed. Gregor, I see large scale seismic information. Yes, that's good. We want to work at large scale. We got stuff where we can look at the structures, straddle correlations, on lap, top lap, and so forth. That's good. Outcrop, you got to love the outcrop, right? Still, we are challenged. Deep learning is hungry. We need really good high resolution, multi-scale data sets to work with for training. Wells, yes, one dimensional though, usually. We often need full 3 dimensions, right? Basim, you agree? I see the nodding. Thank you for participating. I appreciate that. Thumbs up to you too. Now, what we've done is we've developed a whole suite of rule-based models, surface-based models that can create multi-scale training models. They can run a 10 million cell model in literally a fraction of a second. We can build large ensembles of models. And then what we've done is we've tuned these models using outcrop information. This is directly from Kyle Straub. Kyle Straub looked at the compensational index or exponent of outcrops from outcrop deep water lobes. We match that. So we have good models now. Now that we have those good models, we can use them as training. Now, you know, we do a lot of practical applications. Once you have a huge set of training models, it's so tempting to run all kinds of sensitivity analysis. Here's a sensitivity analysis where we looked at a bunch of different types of model parameters and their impacts on hydrocarbon production at different times with significance. But what we're doing is we're usually using these models for training. Let me show you what we're going to do with them. We do need good training models. That coming up with methods to efficiently make a wide ensemble, an uncertainty model, a prior, I would say, thinking Bayesian about it, is very important. We need that. All right, let's talk about how we make subsurface models with deep learning. I have a variety of graduate students working on this right now. I'm really excited about this. We're working on making GANs, generative adversarial networks, that are able to, the generator can produce realistic subsurface models. Here, I'll show you an example. Let me prove it to you. This is the initial GAN realization, you know, random. All of the tuning, all the weights are random. So it's basically just garbage. After many, many epochs, you can see it starts to train. By the end of our training, we're reaching a point where the model matches the training data set that had compensational deep water lobes. This is very powerful, can capture the multi-scale features. This is a simple example here. Now, I told you I was going to prove it to you. Anybody here ever done multidimensional scaling? If you've never done it, I recommend it on the weekend. It is fun. It is a lot of fun. Okay, what we do with multidimensional scaling is we can take all of our models. You see the red? Those are my fake models, my generator, my GAN. These are my rule-based training models. You remember I just bragged about those really good training models? The multidimensional scaling projects the degree of dissimilarity between the models into a low dimensional space, 2 dimensions. This looks like a junior high dance. They're not mixing. You see that? There's no mixing. Now what happens as we train, they start to mix on top of each other. Once we get over here, guess what? Jeff Pyrcz, professor in Stanford, working basically like me. We work in the same area at Stanford. He does. I'm at UT. I love UT. See the flag. Okay. What he says, he suggests that MDS, we can use this as visualizing the uncertainty space. It's a distance-based uncertainty approach. If you look at that, if you accept that, the GAN model is spanning the uncertainty space of the training model ensemble. And that's exciting to me. Now, let me show you, I want to show you something else. This is where it gets really, really exciting.
Is this just a T-SNE visualization or?
Is this, yeah, you're right. It's analogous to that. Yes.
Okay.
Yeah, Adam, you nailed it. Yeah. And I got to tell you, when it comes to uncertainty spaces, very nice, very powerful. I am concerned about the inability to go back and forth though. To me, that's always been a concern to me, and a temptation to use other types of projection methodologies for sure. Now, we can produce beautiful models. Anybody here ever built a subsurface model? This is a GAN model right here, constrained by well data, geophysical information. This is getting to a point where it looks like I'm flying in an aircraft looking down at a meandering fluvial system. Like these are really, really incredible. We're starting to honor the structures. This is also a GAN model right here. Beautiful. The other thing that's very powerful is that when we build these models, this outline right here was conditioning. We condition it to this outline, and the structures that we generated within it were consistent with the outline. This enables true multi-scale modeling. And if we can do that, now we can build models for the subsurface that go across all scales. Slope valley, canyons with channels inside, within other types of structures, structures within the channels themselves. We can go across all the scales all at once. The result is we can truly build integrated multi-scale models, and these are essential to our decision making. Okay, what are we learning? Deep learning, we're pushing the envelope for the degree of complexity. We're also able to get multi-scale models, and we are able to reproduce the uncertainty model. And that's essential to us. I'm going to make a comment on that at the very end. Subsurface forecasting. We've been working at getting fast fluid flow proxy models, surrogate models for fluid flow. We've been working at the very finest scales. Everybody readjust your eyes. You see this sample right here? It's a cube. You know how big it is? That big. Centimeter by centimeter by centimeter. Very small cube. This is a sphere pack synthetic data set. We trained a convolutional neural net. We're using a ResUnet type structure, and we trained it to be able to predict the fluid velocity field, orthogonal X and Y, okay, or X, Y, and Z. So we're able to produce the color right here. Yellow is high velocity, red is low velocity. Everybody can see you got that boundary layer close to the grains. The grains have no velocity. That's why they're punched out. This model, we can do this within a 100th of a second, like very, very fast, make these predictions with accuracy, usually about 15% error is the maximum, relative error. Now, if we try to do this using lattice Boltzmann, we have to run it on TAC on multiple, quite a huge number of clusters, and it takes a day or two for us to use with a lattice Boltzmann solution. We're really excited about this because it actually generalizes. We trained it on the sphere pack. And when we did that, we then ran it on actual digital rocks. Dr. Prodanovich in our department has a open source, open access digital rocks, tomography, imaging of rocks. And so we got cementation. This is carbonaceous, I believe. Complicated. It still worked well in that setting. All right, what did we learn? Well, I think that we're going to be able to move across scales with our flow proxy. What I would dream of is that we can do flow simulation at the large field scale by accounting the pore scale flow. That would be amazing. Right now, we don't. We tend to work at some really large kind of representative elementary volume. Let me talk about uncertainty modeling. Can I make a statement? Let's see who disagrees with me. Would you agree that machine learning has been overly focused on accuracy and not uncertainty? In my mind, what I've seen is much of machine learning has been really focused on. Adam, I thought that might invoke you.
Yeah, yeah. I mean, yeah, accuracy is king.
Geez, you scared me. I totally thought you were going to go after me for that one. Okay, and you know what? I agree, accuracy is important. But do you remember the point I made before? 1/1,000,000th of the subsurface is sampled directly. We live in a world in which the uncertainty model for us is just as important. What we've started to do is we encoded uncertainty goodness in cross-validation into the loss function of deep learning. When we do that, this is it right here. This is uncertainty goodness versus dropout frequency and learning rate for a convolutional neural net. When we use this to build an ensemble of models, we find that there's a critical dropout. This is just a static probability of dropout. Right here, we find there's a zone of good uncertainty models, good ensembles. What did we find? If you take two different models that we tune and we run, if we tune with two different approaches, one where we just focus on accuracy, what we find is that this is cross-validation. We do a great job in accuracy. We're doing fine. The uncertainty model is terrible. May I introduce you to the accuracy plot? It's not too bad. This is a symmetric probability interval of your uncertainty model. This is the proportion of data within that interval. What we find is that this is an inaccurate, imprecise model. If you tune based on uncertainty goodness, you get good accuracy, actually improved accuracy, and you get a good uncertainty model. We're able to do that now. We can build on machine learning, deep learning ensemble models that have good uncertainty models for the subsurface. We have a publication that's coming out like immediately. We're really excited about that. Okay, I'm going to finish there, and I probably ran over time. Verena, I apologize. I was having too much fun. My motivation, the subsurface needs new capabilities and solutions to realize the value in digital revolution. Geoscience and engineering remains critical, and we can augment and build on a rich history and knowledge of data-driven approaches in the subsurface. I'm just excited. What can I say? I've seen this every day, every place I go with my students. I really do see a great opportunity for us to integrate and add. It's a green field. Let's work together. All right, that's it.
Awesome. Thank you, Michael. That was such a wide-ranging talk. Any questions from the audience? We have a little bit of time. We want more Nickelback.
Adam, do you believe me?
I pegged. It's too easy to hate on Nickelback. Come on.
I know.
What kind of? How do you do all your training? How computationally expensive is all this? It seems very expensive. How do you get your labeled data sets? Kind of what's the workflow for this?
Yeah, and Adam, I'm glad you asked that question. I appreciate that. This is why we've been driven to these type of rule-based models that I suggested before. And let me add a couple more details around them. They're actually built by using simplified versions of the physics. We know that rock gets deposited in a certain fashion. We can summarize at appropriate scales and understand kind of how rock gets stacked up. Now, what's fascinating about this approach is it's surface-based and grid-free. It means I can pick any location in the model and I can tell the story of its genesis. I can say, oh, this part of the model right here is a low energy. It was deposited in shallow water with this velocity, and this was how far away you were from the source where the rock came from. You can literally you can use all of that information to build very, very rich multi-scale models. They can be rasterized to any resolution you need them. They're described by continuous functions. Okay, now, if we do this, and these models are very good, then we have this very broad set of training. I can change a dial on that model and it becomes
okay. So you use
model.
kind of a physical simulation to do the training, but then you might ask, well, I guess, but the physical simulation can also be used to do prediction. So sort of what is the what is the deep learning gaining you other than you know, depends on the expense of the physical simulation, I guess.
It is impossible to take that model and condition it to all of the wells, the geophysical, to any type of interpretations, geologic mapping, and so forth, production history. It is impossible, infeasible to do that. What we found is that this projects into a lower dimensional space through the latent features. We're now tuning the model to match production data by tuning latent features, guaranteeing that every generated model is consistent geologically. Up until now, we have destroyed our geologic models when we try to honor the engineering data. We've overcome that through deep learning.
I see.
It's exciting. The lower dimensional space, Adam, is just epic. What we're starting to learn and see through the
because you get to control like the knobs that you really want to control. Yeah. I get it.
So that's one of the things. Now, of course, then there's always the flow circuits, because you say, well, why don't you just run the physics? In many cases, the physics is so expensive.
Right.
You look at, would you believe that the energy companies that do this type of flow simulation, they rival the computational load of many of the machine learning shops, because these are very complicated.
No, I'm not surprised.
Yeah.
I mean, a lot of people, a lot of people in physics are trying to simulate things using deep nets.
Yeah. And
you have a couple questions.
Yeah.
Go ahead.
Okay.
What's the furthest you've been able to accurately predict lithofacies through ML on well logs, and what sort of reservoir characteristics have you found best for ML on well logs?
Yeah, and that's a really good question. What we found is that, well, first of all, it can be very challenging to predict down to lithofacies. You know, because of the fact that lithofacies can be quite variable. Very small scales have higher degrees of variability. We find depofacies we do better. Predicting away from wells, we have the same data sparsity problem. That's been long-standing. That is seismic. It is a non-unique problem to figure out the depofacies from seismic. The great thing from machine learning is that it provides us models that are consistent with the well data and uses the well data in a better manner to make predictions away from the wells, because the geometries are more realistic. The uncertainty model is better. We end up with a better prediction away. So I would say we're able to go further away from the wells, which is really exciting.
Let's see. Well, I guess let me just take one more question here. I mean, Vuong Pham is asking, you know, most of CNN's GANs are effective in image-related data, but the subsurface data is not totally image-related. Several engineering data are stored as tabulated data. How do you address that?
Yeah, and that's a very good question. When we work with the GANs and CNNs, we typically are working with three-dimensional models. Two-dimensional models. It will require this step of building a reasonable unconditional analog training model set to work with is essential for us. Now, we're still doing conditional GANs. You know, we're still conditioning them at well locations. Sometimes we switch to a Pyrcz approach when we want to do kind of specific conditioning. We have a high degree of constraint. And that, if you think about Pyrcz, that's the approach of basically taking an outline of a purse and trying to make a purse, outline of car, make cars. That's that type of approach, image to image translation.
I can tell we're sort of out of time here. I can tell you still have a couple other questions, but they're sort of on the kind of technically, how are you doing a bunch of things. So let me just invite people to, you know, email Michael. You know, I'm sure he would, I mean, the point of these seminars is to, you know, start some further research projects and collaborations. So, you know, maybe you could say one last thing here, Michael, on this question about how you're incorporating uncertainty into the training process.
Yeah. I think a really good quote is this. Jeff Pyrcz at Stanford suggests.
Oh, hold on, they want to know if they should email you via your email or Twitter. I assume it's your email. Do you want to type the email in your chat?
If you can do it, if you want to do it on Twitter, we're all going to be Twitter famous.
Yeah.
We can take
maybe
this
Verena
discussion online, or
can
just
type it.
email me. That's fine. But
What is your, it's on michaelpyrcz.com, right?
yeah, I'm super easy to find, Joel. Like professors can't hide. If you Google
Yeah.
search me, you're going to find
I'm
a
sure if
faculty
you go to
page.
if you go to michaelpyrcz.com, you'll find all.
I can drop an email address for you in the chat if that's okay.
Okay.
Verena, thank you so much. And let me comment on your question, Adam. I think in general, we have always used too narrow of a prior. In the subsurface, we always think we know more than we actually do. We're always surprised by the subsurface. I think what machine learning will do is we're going to realize how faulty that was, because we do a much better job reproducing the information from the training models now with this deep learning. And we're going to realize that we need to have a much broader prior in building our uncertainty models. I think the other thing is that, and I mentioned this already, Adam, the ability to map into a limited set of latent variables on the latent vector is very, very powerful. And it allows us to start to kind of turn very few dials and explore uncertainties. I think this is going to change the way we think of and see uncertainty. But let me just make one comment though. We're still going to struggle. Stationarity, multimodality, the way things, the subsurface changes. These are not simple problems.
Okay, well, again, thanks again for everybody. We're so out of time here, but it was a great talk. Michael obviously spurred a lot of discussion, we'll see. Come to more Machine Learning Lab events, and you'll see more of Michael Pyrcz. And I'll see you on campus soon, hopefully, Michael.
Yep. Adam, thank you very much. Verena, thank you very much. Everybody, stay safe. I appreciate you joining in.